just because. Is going to become very important today, which is one reason why I put it on the practice test, just to get us ready for this. So let's do this first, because this is old news. I want you all to take a minute, and if you don't have a z-score chart, oh well, I didn't really bring it. I need you to figure out the z-scores that catch the middle 99%, let's say. I want to know what the z-scores are that catch the middle 99%. Don't say anything. Just work on it. You can ask a question, I'm sorry, but just don't say the answer. Just let everybody work on the answer. So we did a problem like this before. There was one on the practice test. Just to help you out if you're having a little trouble, there's no way in hell you're going to look up 0.99. This has nothing to do with the answer directly because the chart only understands areas that are where? Below a z-score, correct? And there's two z-scores I want up here. Yes? So I can do either one of them. I normally just do this one because it's a little easier. What percentage is below that guy? Yeah, so there's 99% inside. There must be 1% outside. 0.5%. What's 0.5% as a decimal? Point 0 5 0 5. 0.05 is 5%. 0.5%.
Oh, 0.5%.
Stop for a minute. Is everybody with 99 in, 1% out, half of a percent over there. 0.5%, move the decimal back twice, 0.005. Let me stop. Because does everybody understand all the numbers I just spewed at you? Okay. Yes?
I don't.
All right. Do you agree? Well, you have to agree, because I gave you the problem is the middle 99%. Bang. If there's 99% in there, what percent is outside?
Well, the rest of it.
Which is?
5.
Oh, well, no, don't just look at that. If there's 99% of the people in the house, how many of the people are outside? What percent are outside the house? If 99% is in, what percentage is out?
Well, that would be.
If there's a 99% chance of rain today, what's the chance it won't rain?
1.
Okay, 99% in, 1% out. How much on that side? Half of a percent. Which is, so half of a percent, once, twice, 0.005 is the decimal. So you want to look up 0.005, positive or negative z-score?
Negative.
Negative, because it's over here, right? So if you look up 0.005, what do you get? You should get a little asterisk dude, right? Right? Okay. There we go. What do you get?
Negative 2.575.
Yes. Yes, I got that memorized. 99% is unimportant. You'll see later. Look what we're getting into today. And up here would be what?
Positive.
Positive 2.575. It's in the middle 99%. It's symmetric. Boogie woogie. So therefore, whatever that is, that's got to be the opposite sign. Are you guys with me? This is old news. This problem right here, old news. Old news. We should be able to do that problem with no trouble. Let's try another one real quick. What about, let's just do the next level up. What about 98%? Okay, take a minute and figure out. Don't say anything. So again, you do the exact same thing. 98% in, what percentage out? 2. What percentage on that side? 1%. And it doesn't matter which z-score you find first. Can somebody tell me what percentage is below that z-score? Right? So you could look up 0.99. You'll get the same number. It'll be positive instead of negative. It's the same number, of course. So what do you guys get? You should get a nice, I think it should be pretty close to it, if I remember correctly.
2.33.
Yeah. So you get negative 233, positive 233. So what this means, if I have a normal distribution, and I go up 2.33 steps and down 2.33 steps, right? From my perspective, that was right. Up 2.33, down 2.33. I will catch 98% of the data, right? You guys semi with me? Okay, all right. Again, all old stuff, right? All old stuff. Now, what does this relate to what we're about to get into? Okay. What we're about to get into is this. The first step will still not be completely what we do. In the real world, if we have something we just discovered, we don't know a damn thing about it. So obviously we don't know the population mean, right? And we don't know the population standard deviation. So if we discover, for some reason I've got arachnophobia in my head, I don't know where the movie just came from. We've discovered this brand new species of spider, right? And we're curious the average amount of venom it has or whatever, or the average diameter. It's a little circular looking spider, right? I don't know. You with me? I don't know that. So don't we have to take a sample just to figure out what mu might be, what the population mean might be? So if you come into contact with something brand new, and you're like, I don't know anything about this, you will take a sample to get a feel for what the real thing is. So another real life example of this is there's an election coming up. What happens before elections to kind of tell you how things might go? People conduct polls, right? They call people, they ask them several questions, surveys designed to try to weed out people that could just be lying or whatever, and they try to get an accurate representation of the population through a sample. Are you with me? Does anyone know the percentage who are going to vote a certain way? No, nobody knows that, right? Not even that octopus that predicted every election correctly. I don't know if you guys heard about that. Leaving the octopus out. Nobody knows the real percentage. Nobody has a clue. So there's something we don't know. What do we do to investigate it? We take a sample to get a feel for what it seems it might be. Now, some polls, back in the day, they believed the polls a little too much. And that got people into trouble. So we're not going to suddenly take a history lesson about hanging chads and all this stuff. You can just look up the 2000 election if you want. Yeah, some of us lived through that. It was great. Anyway, sorry. You guys are like, whatever, dude. Okay. So any situation we come into that we don't know a lot of stuff yet, we're going to take a sample to investigate it. So that means we're not going to know the real mean. Every problem we've done so far, we basically had a way, we either were given the real mean, the population mean, or we had a way to figure it out. Correct? No? Are you guys all with me? So far, like in chapter 6 and chapter 7, didn't they just tell us the population mean, correct? And then we did stuff with that, yes? Real statistics, not, that was still statistics, but like your kind of traditional statistics, you don't know anything. So you just start taking samples to figure something out. And then you make inferences about the whole population. How you guys doing? All right. So if I ran into a group of people on an island somewhere that hadn't been contacted and we knew nothing about them, and I'm like, I wonder what the average height is or whatever, right? I would probably be more curious about other things, but okay. So we take a sample of them, and we'd measure them, and we get an idea of the sample standard deviation, the sample mean. Are you guys kind of with me? And the real mean, if we did a random sample, should be close to the sample mean. Are you guys with me? If you take a good random sample of something and you calculate an average, the real average would be expected to be close to that. Are you with me? You with me? So again, and again, I'm sorry if anybody has a major phobia of spiders, but for some reason, if we did discover a new species of spider and we just did a random sampling of these spiders, it would be very unlikely that we just happen to pick a bunch of really big ones or a bunch of really small ones. So I feel pretty good that the sample mean I find will be close to the real mean. Are you guys kind of with me? Especially if my sample is larger, right? If I take a relatively large sample, it should be good. Okay. All right. So, we have, therefore, here's the idea in pictures. I have a real mean somewhere. So if I find this species of spider, there exists an average, we'll just go weight, an average weight of the spider. It exists, correct? It just exists. And I just need to figure it out. So it exists already. We take a sample, or we send somebody who's not freaked out by spiders to take a sample, right? And then they weigh them, and then we calculate the average. You with me? I would expect, if I take a good random sample, I would expect our sample mean to be close to the real mean. What do you think the word close is majorly important here? What do you think governs closeness? What do you think is going to be involved in that? Standard deviation. Because standard deviation is what statistics uses to measure distance. I love it. Are you guys kind of with me?
Yes.
So far, decent? So we are just discussing concept right now. You don't even know what these problems look like yet, which I understand always might put you on edge, but just relax. It's not going to be crazy. So here's the idea. Just giving a sample mean by itself doesn't immediately communicate to somebody what we think it could be within. So we want to improve upon just the sample mean. I want to give somebody an interval. And I want to say, we are 95% confident that this interval contains the real mean. So here's the idea. If I take a sample mean and then I create an interval around that, there could be a certain probability that it actually catches the real mean. Now, let me see. Is it possible that another group comes along and they calculate a sample mean and they get something like here? So when they create their confidence interval, it does not contain the real mean. Does that make sense? They could just happen to randomly collect really small spiders, and they weigh them, and so their sample average weight is way lower than it should be. You with me? And even when they construct this interval around it, it still doesn't quite catch the actual mean. Are you guys with me? How likely would that be if they were taking truly random samples? Should that be likely? Should that happen a lot? No. Can it happen? Yes. Okay. Does everybody kind of understand the idea behind? All right. Now let me get into some more concrete stuff. Okay. So this is just the idea behind stuff. Okay. So the work we just did, building what the 99%, how far you got to go out to catch 99% of the stuff, immediately comes into play. So if I calculate a sample mean and I go up and down a certain number of steps, in fact, if I want to be 98% confident that the interval I create catches the real mean, how much data do I want the interval I create to catch? I want it to catch 98% of the data, correct? If and the example I like to give, and I don't like fish. I don't know if you guys like to eat fish. I don't like to eat fish. I don't like them. They can all stay in the ocean as far as I'm concerned. But it's a pretty good, I like this analogy. if you wanted to be really certain that you catch a certain type of fish, wouldn't you cast a bigger net? With me. So if you know the fish is in this pond and you're like, I want to be pretty sure I catch this fish, you're going to throw out a bigger net. If you're like, I don't care if I catch that certain fish, you can throw out a smaller net. Does that make sense? So the more fish I catch, the more confident I am that I caught a certain kind of fish. Does that make sense? So if I calculate a sample mean, and then I go up and down a certain number of steps, in the case, if I want to be 98% confident that my interval will contain the real mean, I want to go up and down enough to catch 98% of the data. Then I'm automatically 98% confident that I caught the real mean. So here's how this works. I like to build this. Remember this formula here? Right? We're going to use this a couple times in chapter 8. It's a nice starting point to constructing this idea of what we're going to use. So here's the idea. If I run into a brand new situation, there's actually two things that don't make sense up here. But we're going to assume for section 8.1, we're going to assume we know sigma. And I'm going to give you an example in a minute, once we get the kind of formula put out there, because I think I'm at the point now where I got to show you some concrete stuff or you guys are going to slowly go insane. I'm going to show you an example where this actually makes physical sense. Normally you're like, if I don't know the mean, how the shit would I know the standard deviation? Well, I'll show you. So we're going to assume that we already know the population standard deviation. Okay. So starting here, in this equation, we don't know the real mean, do we? So what's the next best thing we can use? What is, say again, sorry? What's the next best thing? If I don't know the real mean, what do we go take? A sample. So then what's the next best thing to the population mean? Sample mean. Okay, so I'm going to replace this with x bar. Okay.
So it's the same equation as x bar?
No. I didn't write the rest of it yet, right? Okay, I'm with you. But am I only going to go one direction? Don't I want to kind of create this interval, go up so many, go down so many? It's built off of that same idea. If I catch 98% of the data, I'm 98% confident I caught a certain data point. In this case, that certain data point is the mean. So I want to go up and down. Ooh, sorry. Just the way I said that, I was like, look at that. And of course, z is just like, I'm z. So I need z there. So if I wanted to be 98% confident, that would be 2.33. If I want to be 99% confident, that would be 2.575. Those are the two we calculated earlier. Correct? Okay. Now, help me. Where would this come from? A sample. We took a sample, correct? It's got a certain sample size. So what has to change? Probably the thing I haven't written yet. And how does that change exactly? It's going to be what it was divided by square root of n. Oops. I'm going to add something that's going to help me out for section A3. So the purpose of a confidence interval is to give a certain level of confidence that it catches the real mean. So I'm going to add a little something. So, and this is not a part of the formula. You don't even have to write this down. It's just going to help me later. The mean is contained in here. The mean is approximated by this. Okay, that'll help me later. So the purpose of a confidence interval, to be really straightforward, is just to improve upon the sample mean. It kind of gives me an idea. So if one group said, so let me ask you this. If one group said, oh yeah, we think that the spider is anywhere from 5.2 to 5.9 ounces in weight. Right? We might breathe a sigh of relief that it's not like freaking pounds or something. Right? Like it freaks going on. Does that feel like that's pretty good interval? All right. What if another group comes along and says, we think it's anywhere from 3.6 to 8.2 ounces? That's obviously bigger, right? So what might have happened between these two? Maybe these guys took less of a sample. Do you see what happens if the sample gets really big? Doesn't this piece get small? If the sample gets bigger, doesn't this piece get smaller? Is that cool? If I divide by more, it gets less. Yes? You guys all right? So if I divide by a bigger number, the result is smaller. Okay, good. So therefore, I would be going up and down less. So if they took a much bigger sample, that might explain why they went up and down less. Are you with me? So maybe that's one reason is maybe these guys took a much bigger sample than these guys. Is that all right? Another thing is maybe these guys sample well, that won't work here. Later it will when we have an S here, but right now it won't work. Right now it would be the sample size, yeah. Okay. So what, yes?
What does the M squiggly line mean?
So this is I'm going to use this later. The mean is approximated by this. Or the mean is caught by this, yeah. So when I go to section A3 and I want to construct its formula, this will help me at that point. So for right now, that piece doesn't matter. Yes?
Would you say that to the left is still the X equals?
No. No. So the purpose of this guy was what data point will I end up at if I go this many steps from the mean? That's the purpose of that formula, correct? So what did I say? If you want to be 98% confident, how many standard deviations do you have to go up and down? We just calculated. 98% confident. How many standard deviations do we have to go up and down? 2.33, right? So if I start at my sample mean and I go up 2.33 of these and down 2.33 of these, I'll construct the confidence interval around it. That interval I'll be 98% confident that interval catches the real mean. Yes?
And then you said, for example, the 3.6, 8.2, that if N increased, that you would go towards that trend?
No.
Or the other way around?
The bigger N gets, the smaller this gets. In fact, let me say this. My sample is my best guess. My sample mean is my best guess. Do you guys agree? Do you guys understand what I mean by that? Can somebody tell me, well, it might be a little too much right now. So the sample mean is my best guess. This is how much I think I'm off by. So not surprisingly, we call this piece of the formula, we call it the error. There's not that many things in E, Jeff. That part of the formula, we call it the error. So it's kind of like, if you ever been to a county fair or whatever, they used to have these people that would guess your age. And they would guess your age and it would be like within 2 years. So plus or minus 2. That's how much error they could be off by and still be right. Does that make sense? So if I want to guess your age within 2 years and you're 28, I can only go from 26 to 30. Correct? That's pretty much exactly what this says. This is my best guess, give or take this much. Because will the sample mean equal the population mean? What would you put your money on if you had to bet?
Equal?
Will the sample mean, any sample mean I take, will it necessarily equal the population mean? How would you bet on that? You would bet against that being true, correct? I would too. You with me? Because almost any sample I take is going to have variations in it relative to the population. Okay. So the sample mean is our best guess, but I go give or take this much. All right. Yes.
So the larger your sample size, the range
smaller this would be if these remain the same.
Could
Yes.
you say the range decreases then?
The width decreases.
The
yeah.
width decreases?
Yeah.
If those both had the same mean, the 5.2, 5.9, 3.6, 8.2, say the mean was the same, could the difference in that range be because of the confidence level?
Oh, that's another thing that could have happened here is if they used two different confidence levels.
And if you go to a greater confidence level, you'll
Yeah.
have a greater range.
So I'll say this. All right, let me do a couple things. we'll get to a concrete problem in a minute. So does everybody agree with me? Going back to the spiders thing, and I'm sorry. If I had two different groups of researchers go out and they collect their own samples, do you agree that their X bars will almost certainly be different? Do you guys agree with me? It would be really weird if they just collected their own independent samples and they got the exact same sample mean. That would freak me out. I like it, okay. So, there's a real mean. Just exists, right? One group gets a sample here, and another group gets a sample mean there. So if I construct my confidence interval, I just happen to catch the real mean. Will I ever actually know that? No, I don't know what the real mean is. This group, when they construct their confidence interval, they don't catch the real mean. Will they know that? No. So what does it mean when I say we're 98% confident that our interval caught the real mean? What that means is if there's a bunch of different groups and they all construct their own interval, 98% of them will actually catch this. 2% won't. So pretty soon in our future, I'm going to have you guys do a problem where you're all going to construct your own interval, and we're going to actually see what percentage of you caught the real mean and what percentage didn't. And my hope is that'll make this make a little more sense. Okay. So what does it mean? So it's just like if I said, if I flip a coin, it's 50-50 chance it's going to be heads, correct? What does that mean? What does 50% probability of heads mean if I flip a coin? What does that mean? If I flip it once, does it mean anything? What is 50% chance of getting a heads when I flip a coin? What does that mean? Does anyone remember? If my internet goes out and I can't watch my Netflix, right? Or my whatever. Can't watch my Apple TV, whatever. And just everything just dies. There's a big old EMP pulse and I'm sitting there and all I got is a penny. Maybe I can flip that sucker 1,000 times, correct? Now what does 50% chance of heads mean? I would expect around 500 heads. It immediately makes sense if I do it a lot. Probabilities make very little sense on a single instance of something. So if there's a 99% chance that something will happen, it could still not happen. Of course it could still not happen. That just means if I did it a lot, 99 out of 100 of them, it should happen. Are you guys with me? Okay. So if I construct a 98% confidence interval, what that means is exactly what any probability means. It means that if I had 100 confidence intervals constructed, I would expect 98 of them to catch the real mean. So that means that my interval has a 98% chance of catching the real mean. And that's much better than the normal chances that I'm right. So I feel pretty good about that. All right, let's do a concrete example, right? We're still not concrete yet. Okay. So here's what I mean about the standard deviation. So let's say that in some country, in some island, we know the standard deviation of of tree heights. You with me? We know it. We know the standard deviation of tree heights is 2.19 feet. You guys all with me? That's just known. But then we go, all right, this one little area here, this one little area there, it's weird things are happening there. I don't know. So we go there and we measure the heights of some of these trees. And we want to know what is the mean height of trees in this area that's on this island. We know the standard deviation of all trees on the island. Are you with me? We know it. It's right there. There it is. That's the standard deviation of all the trees. Now I'm curious about this one little section So let's say we go there and we take a sample of 38 trees, and we get a sample mean of, you could do it, Jeff. Let's do 14.98 feet. Let me stop for a minute. So we actually physically went to the island, right? You guys missed, we fast traveled when we came back. We went there, and then we took a sample of 38 trees in this little area, big area, let's say. And we've got a sample height of this, right? And let's say we want to construct a 98% confidence interval for the true mean height. Of trees in that area. So this is the kind of problem you're going to get. We have everything we need to do this. First really important thing. Remember when we got to 2.33? What were you guys using to get that? Z-score chart, right? When are you allowed to do that? When are you allowed to use the Z-score chart to get anything? It must be what? Normal distribution, 11, right? The picture gives it away at the top of the damn thing. Okay. What is it about this problem that tells me it's normal? Did I say it was normally distributed? Beautiful. The sample size is more than 30. I love it. You guys good? So if the sample size was 22, you officially can't do shit in stats 1. We're getting close to the point where the book doesn't really adhere to that strictly, so I'll point it out when it comes. So our formula to construct a confidence interval is sample mean, give or take, this many steps. It really is just mu plus z sigma. That's the formula we've been using since chapter 2. It's just that formula replaced with sample information, right? That's all it is. So X bar we know. What's the z-score in this case? We calculated that earlier, 98%, right? Confidence interval, so what's the z-score? 2.33, I love it. Sigma I have to give you divided by square root of what? 38. So my advice to you is to calculate the error first, because some problems ask for the error, so you might as well just calculate it first. And it also is easier to do in the calculator if you do that. So maybe I'll show you.
0.3553.
That's the error?
Times 2.33.
Oh, okay.
0.8278.
You guys verify. You never know. Yeah, I'll show you something you can do kind of nice in here. Shit, I didn't want to do that. Okay. All right, so if you do this, so you got 2.33 times, where'd you go? 2.19 divided by a square root of 38. So I get that. Is that cool so far? Yeah. Now this next piece does not matter, but I just want to show you how you can kind of use your memory buttons. Have I even pointed this button out yet? Little stow, so that's short for store. So if I store that number in X right there, because that's the number that I have to do 14.98 plus that, 14.98 minus that, correct?
What's
So-
the difference?
So let me do it again. So if I hit store, and then here's my easiest variable button. Do you see all the little letters A, B, C? Those are all memory locations. You can actually hit alpha and choose any of them. If I only need one thing, I'm just going to use the X button because that's the easiest one to get at. So now the letter X has that number in it. So now if I do this, 14. Here, I guess the people at home, you guys can see too. Whee! This is not that big of a deal, so, but 14.98 minus x, second enter, plus x. So then I get 14.15 up to 15.81.
So you want it to round to the hundreds for the z-star, right?
So here's the idea. I want it to be at least as many decimal places as this was.
Okay.
Yeah. Does that make sense? Again, I could teach this class based on significant figures or digits, depending on what your background is. Has anybody ever heard of those before from chemistry and such? Sig figs or sig figs, I think, is chemistry. Sig digs is math, because of course we have to be different. But anyway. All right, let me do it again. So you do the work, and you get the 0.8276. I have to go back up here. Hold on. Shut and a half. Someday I'll get there. Someday we'll find it. There it is. Okay. There. So I did the work, and then I hit store X. So now I can do stuff with it. And believe me, that's kind of a good little thing to know. It's not, if you don't do it ever, you're fine. You're not going to save that much time. But it's a good thing to know. You can use that idea in a few different places.
How do you get it back?
Say again?
How do you press X to get it back?
You just press X.
Oh.
What do you mean? So that if you hit X, it's going to be that number, right?
Okay, I see.
Yeah. Okay. Okay. Now, here's going to be, how do you guys feel about this so far? So again, the nuts and bolts very often is much more straightforward than the explanation, but that's because it's built off of the idea of you got the concept. Nuts and bolts, pretty straightforward, just plug and chug shit. Now it's going to be the fun part. And when I say that, I'm sure you guys are all like, oh man. You have to interpret what the hell we just got. So, what the hell does this mean? What does that mean? And you're all like, I just heard about this today. Yes.
Question, how do we clear X? Like,
You don't have
if
to worry
we don't
about
wanna
it.
use it again?
You never have to worry about it.
Oh.
What was X before you just made it that? You don't know. It doesn't matter. So real quick, just in case any of you guys are taking any of the math classes where you have to graph stuff, when you do the graph and you put an X in there, it's not the same X. Does that make sense? So this will not mess up anything. If it does, you can kick me in the leg. Okay. And it won't, so I feel fine. Anybody have any? What percentage of the data does that interval catch? 90%. How confident are we that it catches a specific data point? 98% confident, correct? If I caught 98% of the Grossmont students, and I just imagine me, I grew somehow, and I got this net, and all the students are running away, just scooping them up, and I catch 98% of them, how confident am I that I caught a specific student? I'm 98% confident. Does that make sense? Yes, it has to. Okay, good. So here is what you need to write at the end of any confidence interval problem. So you guys have the right face right now, but let me leave this for a minute. We are farmers. No, we are 98% confident that the interval, what is this? 14.15,
15.81.
14.15 feet. I love it. If you don't put units, I'm going to be a dork and I'm going to over centuries, sheep. So 14.15 feet to 15.81 feet contains or captures the real population mean height of trees in this area. That's the whole idea captured in a little statement, yeah.
And you got 2.33 by finding what's closest to 0.98, right?
Well, what's closest to remember, 98%, 2% outside, 1% that side, 0.01, closest was 233, yeah. So you're going to see some of these repeat, because the ones we use the absolute most used percentage for making a confidence interval is 95%. Why does that make sense based on what we've done already? Where did we say unusual starts? 2 steps. And what percent is caught in 2 steps? 95%. Isn't that a 95% confidence interval? I didn't call it that because we didn't know what the shit that was. But if I go up and down 2 steps and catch 95, then I just make a 95% confidence interval. So in this case, they're just redefining where unusual starts, right? There's like, nah, 5% is not good enough. I'm going to make it 2%. Okay. What's the probability that our interval does not contain the real mean? 2% chance, which again, is much better than my normal chance of being wrong, so I feel pretty good about that. Okay. All right. I like how you just accept that, yes.
Wait, but 2.33 is 9901 for a z-score.
Totally,
So
I love it. So that's why it's so fantastic, because if I want to catch 98% and there's 1% here, wouldn't the z-score have 99% below it? Yes, cool. Okay. Okay. I can't remember now. I think, can I see your z-score chart real quick? I don't think it's got things on it. Oh, they do? Okay, let me go borrow this without your permission. No, I'm not, because I don't have the stupid little projector set up. Look at your z-score chart. On the positive side, lower right-hand corner, there's something on what I call the baby chart. I call it the baby chart. Do you guys see how, remember we did 99%, we got 2575? What's it say? Confidence level, 99, 2.575. What are the other ones they list? They list 90, right? 95, 99? 98 is not the most commonly used one. 95 is the most commonly used one, and 90, 99 are the second most commonly used confidence intervals. Are you guys kind of with me? Not at all. Yes. No. Sorry. We're going to get something better very soon. We're going to get something much better than that. For right now, that's a nice little reference, right? Everybody with me? Somewhat. Okay. Now, two things. If I made a 90% confidence interval, would it be wider or narrower? Well, wider or narrower than this one? If I made a 90% confidence interval, does it have to catch more or less data? It's got to catch less. I only want to be 90%. I can catch 8% less. So will it be wider or narrower? Will it have to catch more data or less? Less, so it can be narrower, right? Maybe. Secondly, what if I do all this work and I find out that the average tree height on the island is 16 feet? Does our research indicate that there is something wrong with the trees in this little area of the island?
Yes.
Why?
It's different. It's different.
Good. Our entire interval is how related to 16? Lower than 16, correct? We are 98% confident the real mean of trees heights in this little area goes up to 15.81. So this is evidence that it's not 16. This is evidence that the trees in this little area for some reason grow to less height than the other trees on the island. Does that make sense? Could it mean something's wrong with the water in that section, or something's wrong with the air, or something? Some creatures out there are like, I don't know, actively keeping the trees from growing. There's too many other plants that are sucking the nutrients. Are you guys at all with me? Yes. So again, going back to the idea of Aaron Brockovich and the cancer thing, we know the general cancer rates. So if we find little areas where it is different, if I construct a confidence interval for some sample that I've taken and I see that it does not include the actual, I go, something weird's happening here. Let me kind of focus on this area and test the water, test the air, test the whatever. You guys with me? Okay. Yes, I do say water like that. Okay. All right. Now. Like this. Okay. Next little thing, and then I've got a little worksheet, believe it or not. Looking back at the formula for this. What did I call this piece again?
CI.
No, the whole thing is a confidence interval. It's this piece. Error. That's right. All right. So let me do some weird math person shit. Is that okay? That's the error, right?
Yeah.
Here's the idea. I want you to understand. What if I needed to be closer to the real mean? What if this is too wide? How big of a sample would I have to take to make it a certain amount narrow? Are you guys at all with me? If I take a sample of 38, doesn't that result, and I just went against my own, what was the error here again? I can't remember. 0.8. There it is. 828 roughly. Is that cool? If I take a sample of 38, that is the error I get. If I want to make the error smaller, don't have to make the sample size go up. What if I wanted the error to be 0.5? I want to be within half a foot. How big of a sample do I have to take? I don't know. I just know it's more than frickin' 38. Does that make sense? So I want to construct a formula that if I plug in the error I want, it spits out the sample size I need. This is what we call a feasibility study. If I want to be within so close to the height of a tree, and the answer comes out to be 1 billion trees, that is not only not feasible, it's also probably not possible on this freaking island. It's not 1 billion trees. Are you guys kind of with me? Then I'd let go of that. I'd say, well, that's a pipe dream. I can't get that close. All right. How do I solve this for n? It's basically everything I just said. I want to solve that for n. Oh, shit. A very useful thing from algebra. So watch this. I'm going to do... First, I'm going to make sure people at home can see this. This is going to seem really unrelated for a second. What is 10 divided by 2? What? All right. What's 10 divided by 5?
2.
Oh, so these can just change places, huh? Right? If I divide 10 by a chunk of it, I get the other chunk of it. Does that make sense? So watch what that means for me in algebra. I can just switch these two. Yeah. Oh, yeah. Wow. Yeah, I know. That's the most, it's not David Blaine shipping. That's the best I can do as a math teacher. Look at that. Ooh. And then you know what's the last thing I have to do to get n by itself? Square both sides, right? So real quick, let's actually do the work I just hinted at. We already know that if I take a sample of 38 trees, I get an error of 0.828, correct? If I put 0.828, Jeff, if I put 0.828 there, I know this is going to be 38. Are you with me? If I put a 0.828 in for the error, I already know that needs a sample size of 38. You guys see that? What error do I want? What did I say? I want to be within half a foot now, right? What sample size do I need to be within half a foot? Do you guys understand how that's the error within? Within is plus or minus. So a key word for error would be within or off by. Does that make sense? You might see any of those phrases. Okay. Do we know what z was? Yes. What was z? 2.33. Do we know what sigma was? Thank you. And then we know what the error wants to be. Half a foot, 0.5. Can somebody do that for me? You can see it. This place is not really set up. I don't like using the projector.
10.205.
Did you square it? Let me put this up here. Equals 38 leads to an error of 0.828.
104.15.
That's 4, 8. She get around 70 or something, I'm thinking.
We're at 104.2.
On 100? Okay.
104.15.
That's me estimating. 100 and what now?
4.15.
And you always just round up because you don't want to take 0.15 of a poor little tree, dude. Let me see if this makes sense. When we took a sample of 38, our error was 0.828. We all saw that happen. If I wanted to make that half a foot, off by half a foot, I have to take a bigger sample. Why does it make sense my error goes down if I take a bigger sample? Less variation. Right. I should be, if I take a larger sample, shouldn't I be getting closer to the real mean? If I take a sample of 2 Grossmont students at random, couldn't their average age be just about any damn thing? If I take a sample of 1,200 Grossmont students, random sample, I'm putting a lot of money that is really close to the real average. Does that make sense? Okay. So of course, if I take a larger sample, my error is going to go down. In this case, to make an error of 1/2 foot, the sample has to be 105. So I'd have to take, what was it, 38? I'd have to take 67 more trees if I did that right in my head. Because how many did we take in the first place? 38. If I now need 105, I could just take 67 more trees. And then I could be within 1/2 foot. All right, let's see how this goes. Okay. This one talks about dolphins. Much better than spiders, I guess. I don't know. Nothing wrong with spiders. Oops. Anything.
Thank you.
Anything. Let's see who's got this space. All right. So go ahead and try to. The one that says section 8.1, don't try the one that says section 8.3, because we haven't talked about any of that yet.